In this video, we're going to be looking at Bernoulli differential equations, and I'm going to do a derivation which converts the Bernoulli differential equation into linear form. So, the general form for Bernoulli differential equation, as we've seen before, looks like this. The difference between this and linear, if I put this here, is that you have a y to the power n. And that n, remember, can neither be 0 or 1. So what we're going to do is we're going to convert the differential equation into linear form. And I'm doing it for the general case here, because if you want, you can use the final formula as is at the end of it. You don't actually have to go to the derivation each time. And I'll show examples of how to do that. So, I'm going to convert this into linear form, as I said, and I'm going to start with the rightmost side of the equation. You'll see the difference between Bernoulli and linear is the y to the n, which means I'm going to divide through by y to the power n. So we do that, y to the power n. So which means we're going to get 1 over yn dy dx, p times 1 over y to the n times y, q y to the n 1 over y to the n. If I simplify and use exponential laws to change that form, you'll have an equation that looks like this, is equal to q. Okay, so our right hand side looks like the linear differential equation. We go to the next term on the other side of the equation sign. If you look at your linear, your dependent variable is to the power 1. Right? In the equation that we're working with in Bernoulli, we don't have that. So we need to change that variable. And I'm going to do that by saying let z equals to y to the 1 minus n. Right? So therefore, your equation will change. Pz equals q. Okay, so now you have a dependent variable to the power 1, which means it is linear in the dependent variable. The next thing we have to look at, the first term in the equation. If we look at the linear form here, you'll see that your dependent variable, which is to the power 1, matches up with the first derivative that you've got. So you have to do the same thing for the Bernoulli equation that you're converting. You have to have in your first term a derivative where your dependent variable, you're finding the derivative of the dependent variable with respect to your independent variable. So that's what you want there, so that it matches up the same as in your standard form for your linear differential equation. Okay, and we can do that because we know what z is. So, from z equals to y to the 1 minus n, in order to find dz dx, we use power rule. So the 1 to the minus n comes to the front. You have your power minus 1. In this case, because y itself is dependent on x, you still have to find its derivative, right? Which simplifies to 1 minus n y to the minus n dy dx. Okay, so if we look at dz dx, remember that that's what you want your first term to be. So this term here, you want to be dz dx. If you look at the difference between dz dx here and the one up there, the difference between those two is that at the bottom you've got 1 minus n, but you don't have it in the equation that you're trying to convert. So, because 1 minus n is just a constant value, you can introduce it to your equation. So if I call that 1, you'll have 1 multiplied by 1 minus n, which means you'll get 1 minus n, y minus n dy dx, p 1 minus n z 1 minus n times q. Okay? So that means that your first term is the same as dz dx. So you've got dz dx, p 1 minus n times z, 1 minus n times q. Right? Where your first term is equal to that one there. Okay? And that is now in linear form. To make it more clear that it is linear form, I'm going to change this expression in front of z, and I'm going to call it t, and I'll call that one s. Right? So that p is that t, and that expression is that one there. So there it's easier for you to see that you do in fact have linear form. Once you've converted your differential equation into linear form, you can now use the linear method in order to solve. Okay, so now I'm going to do an example where I go straight to using this equation here. Okay, so let's look at an example. So in the example, you'll see our dependent variable in this case is y and your independent variable is x. Remember, of course, that in other examples, you don't necessarily have to have those two variables. So you have to be able to work with different variables. Okay, so in the example, we have what is a Bernoulli differential equation, and you know because you've got your dependent variable in two different places. Okay, on your right-hand side, you've got y cubed, and on your left-hand side, you've got the power y. So this is what the Bernoulli form looks like. So you'll see that it's very close. Right? You'll see there that it is very, very close. You've got your y's, and you've got y to the n. In this case, 3 is the n value. But the difference between these general forms is that you have an x value in front of the derivative in your example, whereas in your standard form you only have a 1, which means that you need to get rid of that x value. And we do that by dividing through by x. So you'll have dy dx 2 over x times y, x to the 6, y cubed. Okay? So then, in this case, n is going to be 3. Right? Okay, so if we look at the equation that we've gotten previously, we want to convert this form into linear form because now we've got the general form for Bernoulli. Right? And our general form for the linear equation that we converted looked like this. Times z 1 minus n q, where z is y to the power 1 minus n. Right? And dz dx was 1 minus n y minus n dy dx. Right. So in this case, In our example, we have that n is 3, right? N is going to be 3, which means that your z value is going to be y to the 1 minus 3, which means it's y to the minus 2. Your derivative is going to be 1 minus 3, y to the minus 3, dy dx, which means it's going to be minus 2, y to the minus 3, dy dx. Right? If you substitute these values into your general form here, you're going to get minus 2y to the minus 3 dy dx. P in this case is going to be 2 over x. All right, there we go. P is going to be 2 over x. So we'll say 2 over x times minus 2, z equals minus 2 q, and q in this case is going to be x cubed. I actually don't have to write q there. You can say x to the 6. Right? So then your first term becomes, that first term there becomes dz dx 4 over x times z equals minus 2x to the 6. Right? So now we have your linear form. You've converted it into linear form. Once you've got that, you can then solve the linear differential equation. Now you'll see that this method needs a lot of memorization. And for me, I personally find it a bit confusing. So I prefer doing the method that I showed in class. In the next video, I'll show that method using the same example and solving the entire problem.